Hi everyone. I'm addressing your feedback from today's discussion about chemical factors for solubility. It seems like I had a good number of comments basically saying we're still having some difficulty trying to identify when ions are going to be more soluble in an acidic versus a basic solution. Could you do another example? So yeah, absolutely. Let me give an example, or give an example question here. So which of the following salts do we think the solubility is going to depend on pH? I give you three options here: silver fluoride, silver chloride, or silver bromide. So take a moment, see if you can pick which one, and more importantly, see if you can explain why, like the actual chemical arguments for why that substance should be less soluble, or more soluble for that matter, at high or low pHs. Okay, so it's going to be silver fluoride. So let's think about this. Every single one of these salts, so they all have the general form silver and then some halogen ion. They are all dissolving into solution, forming silver plus, and then this halide ion in solution. And the way we decide which of them are going to be pH dependent is basically deciding, okay, which are any of these ions, the fluoride ion, the chloride ion, or the bromide ion, are any of them going to react with acids and bases? Again, today's arguments about solubility and chemical factors are all based upon Le Chatelier's principle that basically says, okay, what's going to drive this reaction forward? What's going to increase the solubility? Well, anything that might lower the concentration of your dissociated ions. The way you could lower its concentration is if you react with it. And then if you react with that ion, then it's no longer present in solution, its concentration drops, and it goes forward. So we then have to ask if it's going to depend on pH, meaning if it's going to depend on hydronium concentration or hydroxide concentration, if you prefer. You basically need to ask which of these are going to react with acids. And really, there's only one that's going to react with an acid or a base, which is the fluoride ion. The fluoride ion will react with hydronium ions and produce hydrofluoric acid and water. So I've written this kind of like an equilibrium reaction. I mean, it has a forward reaction and a backwards reaction, but I've written it specifically by saying the forward reaction here is much more favorable. Now, how do I know that that goes to completion? Is that HF is a weak acid. The reverse reaction in this case is not very favorable. Most of the HF molecules in a sample of hydrofluoric acid do not dissociate. Most of them stay as HF. So this forward reaction is very favorable. So if I take silver fluoride and I put it in an acidic solution, okay, some of the fluorides dissociate. Those fluoride ions react with hydronium ions. That will have the net effect of decreasing the concentration of fluoride ions, which shifts this reaction forward, so the solubility increases. Now, why does that not work for the other ions, like chloride and bromide? Why don't they react, or why are they not pH dependent? Because chloride is the conjugate base of hydrochloric acid. If I react them, this reaction happens. So I get HCl as a product as well as water. But what I will do here is, very similarly, I'll write my equilibrium arrows here so that it's a little more evocative. HCl is a strong acid, meaning it would very happily donate a proton to water. So actually the reverse reaction here is much more favorable, and the forward reaction is not favorable. And again, that's because HCl is a strong acid and HF is a weak acid. So if HCl is a strong acid, meaning it completely donates protons, then what it becomes, its conjugate base, after it's donated that proton, doesn't really want to take them back. So I can put chloride ions into solution, and even though I have a lot of hydronium ions present, they will not to any great degree react with chloride ions, so their concentration is fixed, which means the reaction doesn't shift forward. Nor does it really shift backwards. I can't take any protons away from this. I can't add any protons to it, so it's not dependent on pH. So along those lines, so that's another example here. So a couple of questions that are based upon this. Somebody asks specifically, why is the chloride ion not basic? I hope this clarifies why chloride is not basic. It is a base in the sense that it is the conjugate base of a strong acid, but hand-wavingly, I would say that it is not basic in the sense that it does not very readily accept protons. It does not accept protons, and we know that because its conjugate acid is a strong acid. That strong acid would much rather donate a proton and exist in the form of chloride and not the other way around. So why is it not basic? Because it's the conjugate base of a strong acid, and the conjugate bases of strong acids are, I would say they are very, 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 very weakly basic, so much so that you don't need to think of them as being basic at all. So that's what I would say. Versus if you have an acid that's moderatively strong, meaning it's a weak acid, its conjugate base is a moderately strong or moderately weak base. So that one will go back and forth, and that's a little bit more. I suppose I should be, if I were going to do these maybe a little bit more reasonably, I would make this one really, really short. So it doesn't go that way at all. It almost entirely goes this way. This reaction mostly goes this way, but it can kind of go this way. So fluoride has the ability to act as a base. Chloride does not. So I hope that answers your question about why chloride is not basic. Following these lines, I had a question. Do we need to memorize the tendency of common ions to be acidic or basic? I hesitate telling people that they need to memorize things. I would say short answer, yes. Short answer, yes, or at the very least, I will give you some hint. So case in point, I would say that it's reasonable, and I've said this multiple times in my videos, so I will reiterate it again. I think it's reasonable to ask you to know the strong acids. So hydrochloric acid, hydrochloric acid, hydrobromic acid, hydroiodic acid, perchloric acid, sulfuric acid, nitric acid. Those are all strong acids. So if I see any salts where I have a metal and, say, the sulfate ion, that's not a good example. I'll do the nitrate ion. Nitrate ion is not a basic ion because it is the conjugate base of nitric acid, which is a strong acid. So we can predict that its conjugate base is not strongly basic. So do I expect you guys to memorize these things? I expect you guys to know the strong acids and know the strong bases. I expect people to understand that the conjugate bases of strong acids and bases, their conjugate bases and acids are not strong. They are not acidic or basic. That's what I would expect people to know or memorize. Beyond that, and I would say it's fair to ask you to memorize maybe a handful, a very small handful of weak acids. Hydrofluoric acid, I expect people to know that that's a weak acid. Ammonia, NH3. I would expect people to know or be somewhat familiar with the idea that NH3 is a weak base. But beyond that, no, I don't normally ask people to memorize. So I will try not to have questions where those are assumptions. But are you required to? No. Do I recommend you learn them and kind of have some passing familiarity with them? Yeah, definitely. Definitely know and memorize the strong acids and understand the consequences of something being a strong acid. Along the lines of memorization, do we need to know the solubility rules? No, you do not need to know the solubility rules in the sense that I will not be explicitly testing you, give you a compound and ask, is this compound soluble or insoluble? I certainly will not ask questions like that. Now, so in that sense, you don't need to memorize the solubility rules. That being said, you might find it beneficial to at least review them. Because there are cases where it would be helpful or you can gain a little bit of extra insight or instinct about a problem if you're somewhat already familiar with solubility rules. So along those lines, let me actually answer another question that somebody had, which is, when do you know that multiple reactions affect when do you know that multiple reactions affect the solubility of a salt, and in what way do you apply them? It is hard. It's hard to know ahead of time whether something is going to be affected by a potential reaction. So how do you know? Well, you may have some instincts. You may have some base of knowledge about things being acidic or basic. If they're acidic or basic, then they will tend to react with bases and acids, in which case their solubility is pH dependent. If they have a tendency to be insoluble, form precipitates with other ions present, then that also tells you about a reaction that can occur. And again, you might know that if you know the solubility rule. So let me give you an example. So silver hydroxide. So a question I might have is silver hydroxide going to be more soluble in, how do I want to do this? In HCl or nitric acid? So I've got these two strong acid solutions, and I'm trying to dissolve silver hydroxide in HCl or in nitric acid. And my question is, yeah, which one is it more soluble in? So take a moment, make a prediction, think about, okay, what is going on in this solvation process? What is going on when silver hydroxide dissolves? Are there any reactions that might affect that equilibrium? Oh, I'm sorry. Silver hydroxide actually only has one hydroxide ion. So take a minute, make a prediction if you think it's going to be more soluble in HCl or nitric acid. So make a prediction. Okay, so I'm thinking that there's one of two options that people thought of. One prediction that people might have made is that it's equally soluble in both of these substances. They're both strong acids. If I didn't tell you what the concentrations were, but they're both strong acids. So if we assume they have the same solubility, or they have the same concentration, first of all, I expect silver hydroxide to be more soluble in these substances than in pure water. Because, again, these are both acids. They both provide hydronium ions. Those hydronium ions can react with the hydroxide ions from the silver hydroxide and neutralize to make water. That's going to tend to have a way of removing hydroxide ions, so that's going to shift the reaction forward. And if we're only thinking about the acid reactions that can occur, then you would predict that these are both going to be, the silver hydroxide is going to have equal solubility in either of them. But actually, it's a little bit more soluble in hydrochloric acid. And why is that? The reason for that is, okay, hydrochloric acid exists as hydronium and chloride ions, and chloride ions will tend to react with silver ions and produce silver chloride as a solid, because silver chloride is an insoluble compound. If we were familiar with if we were familiar with our solubility rules, then you can predict that, okay, silver should complex with chloride. That's going to remove chloride from solution, and then the net results here is that you have a even greater push towards the silver hydroxide dissolving, because there's two ways that you're removing products of this reaction. That you're doing it both from the acidic behavior of HCl and the tendency of the chloride ions to react with silver ions and pull them out of solution, which causes the silver hydroxide to dissolve. So this one is actually a little bit interesting, because you'll see first a silver hydroxide precipitate, which is eventually going to convert into a silver chloride precipitate. But we'll still say that the solubility of silver hydroxide has increased and has converted in that way. So when do you need to know? It depends on the nature of the problem. And so I will say this is a tricky problem. It's a higher level question in the sense that, yeah, you need to know quite a bit more information about the behavior of these reactants. And so the more knowledge that you have, the more instinct you'll be able to apply for questions like this. So I figured I would end this feedback video by doing one more example, not example question, well, somewhat of an example question, but let me pose a problem to you, or pose an observation to you, and see if we can explain the observation. And again, this, well, let me show the observation here. So sodium sulfate, Na2SO4, is more soluble in acidic solutions. Sodium bisulfate, HSO4, is more soluble in basic solution. So an acidic solution being one that has a high concentration of hydronium ions, basic solution being one that has a high concentration of hydroxide solutions. Acidic solutions are going to be donating protons, basic solutions are going to be removing protons. So how do we explain these observations? So what I would do is, again, I think about this in terms of Le Chatelier's principle. So I need to know what are the equilibrium reactions that describe the solubility of these two salts. So the first one looks like this. I have sodium 2 sulfate as a solid that dissociates into two sodium ions and a sulfate ion. And I also have the dissociation of sodium bisulfate. No, there's no negative sign there. So that's going to sodium plus and bisulfate. So let's think then about, okay, what type of reactions are occurring here? In an acidic solution, we've said sodium sulfate is more soluble in an acidic solution. So what type of reactions could occur between an acidic solution, hydronium, and either of these ions? Well, the sulfate ion, that can react with acids. It can react with hydronium because sulfate is the conjugate base of sulfuric acid, or it's one of the conjugate bases of sulfuric acid. So you can get a reaction like this. Actually, yeah, I'll do it like this. So that reaction is relatively favorable. The K for this reaction is about 100. So that one is quite favorable. So if I put sulfates in an acidic solution, they'll tend to gain protons, meaning that their concentration goes down. If the concentration of the sulfate goes down, then this reaction is drawn forward, meaning the solubility increases. So that's how I rationalize why the sodium sulfate is more soluble in an acidic solution. It's because, again, there's a subsequent reaction that can occur that removes one of the constituent ions from solution and then drives the dissolution process. What type of reactions can occur for sodium bisulfate? HSO4. HSO4, what is that going to react with? HSO4 could react with acids, but not very favorably. Well, I'll explain why in a second. A more favorable interaction for HSO4 is an acid. It will tend to react with hydroxide ions and produce SO4 2-. And that reaction, I have to admit, I don't know what the K value for that is, but hydroxide ions being strong bases are going to very happily take that proton. So this reaction goes forward. That's what you're going to get from a basic solution. So you'll lose sulfate ions, and that will drive this reaction forward. Now, if you're astute, you might also note that, okay, HSO4 is the conjugate base of sulfuric acid. So you can have a third reaction here that could occur, which is a reaction between H2SO4, water, and then you get HSO4 minus plus hydronium. So, for instance, you could think of a reaction that occurs between acids and HSO4 that would give you a way of losing HSO4 and producing sulfuric acid, and then you might predict that this substance would be just as soluble in an acidic solution as it would be in a basic solution. Except that that's not the case. This forward reaction here, sulfuric acid is a strong acid, which means that this forward reaction is much more favorable. Sulfuric acid is kind of weird. It's a polyprotic acid, and its first proton is a strong proton. That first proton comes off very如readily, and it's a strong acid. The first proton is a strong acid. The second proton, if you try doing, I'm going to run out of board space here, so I'll do it up top. The second proton, HSO4, is not very strong. I mean, it's pretty strong. I mean, the Ka for this is about 0.012, so it's not negligible. It is not very large. So the point being is that HSO4 is a better acid than it is as a base. So HSO4, if it's a better acid than a base, it will prefer to react with bases. I'll say that again. HSO4 is a better acid than a base. If it's a better acid, it would tend to react with bases, which means that you're going to, if you want to remove HSO4 from solution, the best way to do it is by adding a base. That will react with it, that will reduce its concentration and drive the reaction forward. If you try putting sodium bisulfate into acidic solution, you can get a reaction to occur. You can get, let me see here, you can get this reverse reaction to occur, but it's not favorable because, again, the forward reaction here is much, much more favorable because sulfuric acid is a strong acid. I mean, that's a little bit backwards logic. We say that it's a strong acid, meaning that that forward reaction is favorable. So that's just another example about, yeah, things can get a little bit complicated. And it does take, you do need to think about all the other reactions that can occur. Usually they're not as complex as this, but these are things to consider, and there's no limit to how complex they can get. But yeah, usually we'll only think about one or two other potential reactions that can occur. So I hope that addresses some of the concerns people had today. If you have others, I will be in my office. I'm not going to be in the office tomorrow, Tuesday, but I will be here all day today, and I will be here on Wednesday and throughout the rest of the week. If you people have questions, I would be happy to answer them. Otherwise, I will see folks on Wednesday. Have a good day.